I'd like to introduce Cheng Wang to give the presentation. He is the Senior Vice President for Software Architecture Engineering at Logix, where he's a co-founder there. And he's been managing the architecture and software project there for some time. And previously has been chip designer on several other projects and companies as well. So I'd like to turn things over to Cheng to start the presentation. Go.
Thank you, Linley, for the good introduction, and good morning, everyone. It's a pleasure to be here. It's the last day of the talk, but of the conference, but I still have something I think is very exciting for you guys. And today I would like to describe our Inference X1 high-performance inferencing for power-constrained applications, as well as size-constrained applications, specifically as an M.2 card with a reduced power envelope. Actually, I'm having trouble seeing myself here. Just give me a second.
Yeah, we can see you.
Yeah, I just can't see myself. That's okay. So now a quick recap on the X1 silicon, which I had the pleasure to introduce to you guys last fall. It is designed for high throughput edge applications, specifically targeting, the most throughput per millimeter square, as well as the most throughput per watt of power consumed. A quick recap on X1 silicon. It is designed for, of course, high throughput edge applications, namely the highest throughput per watt and the highest throughput per millimeter squared. In addition to that, it's not just high throughput at any batch size. We're specifically targeting batch size of 1 to get to the lowest latency possible. And in addition to that, we do the high throughput, high efficiency inferencing with very high accuracy. So we do not trade off accuracy for throughput. And I'm referring to two things on the accuracy front, both the numerical accuracy, where we maintain the full numerical precision of the model, let it be BF16, int16, or int8, and even extending the precision in silicon so that accelerations such as Winogrand mode can remain lossless. And I'm also talking about model accuracy as a second aspect, because the X1 is really architected for large models and megapixel images that customers actually want to run. Unlike some vendors, there is no limit on model sizes, on the number of parameters. Of course, it has to fit into the DRAM chip, but the DRAM capacity is easily expandable. And obviously, there's multi-chip solutions, which I will talk on later. So, for example, YOLO V3 has 62 million parameters. And we do not force any requirements for sparsity or pruning in order to run them on the model. We run them exactly as the numerical computations would result in. And all of this high performance, high accuracy, low latency inferencing, this level of performance on large models is achieved with relatively small die and a low power envelope. In fact, as we see here, this was just 54 millimeter squares on TSMC 16 nanometer, the one that is running YOLO 3 on the right. And again, the focus here is not that it's running a particular model. Really, we've demoed YOLO quite extensively, and you could even use this off the shelf for your applications. But the fact is that Inference X1 is able to run large models with high resolution images on a small die with single-digit watts of power consumption. And as you can see on the die, most of the silicon is our reconfigurable tensor processor, right, with 4K max and 2 megabytes of L2 SRAMs to store activations, most intermediate activations. And this occupies about 80% of the area. Now, the remaining 4 megabyte of L3 scratchpad is primarily used for caching the reusable configurations. As we know, a lot of graphs have repetitive operators in them. So our chip is configured layer by layer on the fly, but is statically compiled at compile time. So the compiler will statically allocate certain configurations to be cached in these SRAM slots here. So it could be reused later by later configurations without loading them from DRAM again to further reduce DRAM bandwidth. The DRAM It's just a minimum size LPDDR4X by 32. The DRAM interface does take up a lot of pins, especially for a small chip and a small package like this. But we architected it that way because we need the DRAM, and it's critical for scaling the models to what, to beyond what could fit just in the on-chip SRAMs. And you also see that we architected just 4 lanes of PCIe, Gen 3 or Gen 4, so the X1 can be compatible in the M.2 form factor. And of course, there is our eFPGA on there doing housekeeping purposes. We do not have a processor on the silicon. This is executing the housekeeper stuff as a processor. And currently, this is our single chip PCIe. We call it the X1P1. It's one chip per PCIe card. And you see that there's a lot of components missing. Because those were the debug components and headers that we were using for initial bring up. This is the Rev A0 of our board, and of course A0 of our silicon. And we're very proud to be taking A0s into production. So X1P1 being a half height, half length PCIe card, it is the same size as, say, the NVIDIA Tesla T4, which is another inference accelerator. But we fit into more slots because we only need a by 4 connector instead of a by 16. And of course, we come in at a fraction of the TDP. And as I've covered in the talk from last fall, X1P1 offers superior throughput per watt and throughput per dollar on models that customers actually are running, and their own models, or like vision models that they actually care about. But here, I actually wanted to point out that the X1 silicon is designed on a 21 by 21 millimeter package with actually just a minimum set of components when you kind of overlook all the debug pins that are no longer being populated with components. And the reason for that is we really want to target an even smaller form factor. And that's where the X1M comes into play, because some customers, they want to further miniaturize the footprint of the X1 card due to their end applications. So you see this 21 by 21 package on the X1 fits perfectly onto an M.2 card that can only be 22 millimeters wide, especially, the standard 22 by 80 or the 22 by whatever cards are all 22 millimeters wide. So you can see here a side-by-side comparison of footprint differences. It's quite a drastic difference, obviously, between the two cards, and they're on the same scale. But you do see on the M.2 card, the X1 has been rotated by 90 degrees because the DRAM needs to come from the same direction. There's also a large power difference between the two. The M2B.M card is spec limited to 8.25 watts of TDP. So in essence, the X1M form factor brings inference to mechanical and power constrained applications. And it provides customer a faster path to production RAM, because now they can buy this, X1M card that's highly miniaturized off the shelf instead of designing their own custom cards. And of course, another benefit of miniaturization is higher compute density. The customers can get more now throughput in a given volume with only a 17.6 centimeter square of footprint on the M.2 card. And the X1M can be further throttled to fit different power and thermal requirements to give customers even more flexibility based on their end application. So you see here the performance of YOLO V3 at different resolutions at the 8.2 watt, 7 watt, and 6 watt TDP. But as we note here, even the 6 watt TDP X1M can run a heavyweight models like YOLO V3 at a good resolution with less than 75 milliseconds of latency, which is pretty much real time. And to clarify, these lower TDP numbers are not yet accounting for the further savings that we can get from VDD lowering. Since dynamic power reduces as VDD squared, and of course leakage power is exponential to VDD, even a few percentage points of voltage reduction can result in a substantial power savings. But And since at the lower TDP cards, we don't need all the performance that X1 offers, it makes perfect sense. But this is something we're still actively working on. We're starting with just 8.2 watt because we're always targeting the highest performance to sort out all the performance issues on the system level first. And another benefit that we can see here of a higher compute density is actually we can put more devices in these edge servers. So even if you're not, constrained on the form factor, it might actually still make sense to go to an M.2 kind of form factor. So we see here there's an edge server which is 1U form factor, but it has 30 M.2 connectors in the front. Way more connectors than most of these servers have for the half-height, half-length PCIe cards. So overall, actually, these edge servers with many X1M cards can outperform the ones with X1P1, despite having a lower performance per card due to the limitation on the TDP in the M.2 form factor. And another thing that is enabled in the software is graph partitioning across multiple X1 devices. As our colleague Jeremy spoke of yesterday, right? The X1 Inference compiler is responsible for partitioning the graph between layers, so each layer can be reconfigured during execution. But in this case, it can also partition the graph between chips. So each chip can be responsible for executing only portions of the layers in the graph. And the throughput benefit of the multi-chip partitioning is actually very clear. As you can see here, by pipelining kind of the graph as two partitions across two devices, we get almost double the throughput with just two X1M cards. And this becomes even more important, say, when the customer model gets very large and we're starting to, getting to the limit of what the DRAM can hold. This can easily allow you to scale up much faster for those huge models that people may want to run while still using a very low cost and low power device like the X1. And of course, the software is key, right? So the benefit of the multi-chip partitioning is clear, but the X1 compiler suite actually makes it so that the user does not need to do the work manually. In fact, the X1 compiler suite, it automatically accounts for the number of X1 devices in our system configuration. So when the graph compiler, as you guys saw yesterday, the flowchart that Jeremy has presented, when the graph compiler takes the Onyx or the TF Lite model, it starts to analyze the graph and analyze the number of devices that our system have. And then what it will do is it will try to partition the graph optimally. And there's many metrics for that optimization. First thing that it will try to do is it will try to balance the workload across multiple devices, right? So that, not a single device becomes the throughput bottleneck for the whole system that's inferencing in the chain. And of course, when you decide where to make the cut, you want to minimize chip-to-chip communication. You certainly do not want to have the 4 lanes of PCIe be the bottleneck. And generally, that's very, very far from the bottleneck. Because when we look at a lot of these machine learning models, the activation sizes reduces pretty drastically as it flows to the graph. So usually by the time you're partitioning the graph some point down the line, the activation function has been significantly reduced. But still, it's something to take into account for because latency is also important, right? And the chip-to-chip communication time, it directly adds to the latency budget for the customer model. And another thing is configuration reuse, right? Each chip only has so many lines of cache that we can use. So if we can group the similar layers to execute on the same device, then we can actually get more cache hits and have to load less frequently a new configuration from DRAM and basically just maximize the amount of reuse that we can get from a configuration that's already sitting in the SRAM cache because it's been loaded by the previous layer, right? And of course, once the graph partition has been taken place, it maps down to the operator compiler, as we have seen previously. And then the point after that is a soft logic EDA, which is our own proprietary, really high performance place and route tool, because we're targeting 809.33 megahertz on what's essentially an FPGA fabric, which is much, much higher than what the existing FPGAs can do nowadays. But that's really the topic for another day of a conference discussion if I really want to go into it. But in the end of the day, right, the binary NCF file gets generated, and that's what gets loaded into the customer's runtime API for their embedded application, as our colleague Jeremy has spoken of. So basically, no manual partition, no manual work of the compiler. In fact, no compiler experience at all is required to use our software to partition and run the graph. And the X1M card itself is not available till later this year, as you'll see on the next slide. But our unified X1 compiler framework means you do not need to wait for the X1M parts to start your development, right? Everything goes through the same compiler flow. You can start now with our compiler suite and runtime API and try out the models on X1P1 cards before migrating to the X1M cards once they become available. And just to walk you guys through this timeline very quickly, right now the runtime API is available on Linux devices, Ubuntu, CentOS, right? On compiled NCF models, because the entire compiler suite hasn't been released yet, but we have been compiling models on a case-by-case basis to get the binary running, and then the putting it into the runtime to run on like an edge server or like a desktop machine with the X1P1 card inside. And the next quarter, we will be releasing the X1 compiler suite for X1P1 and X1M to support the common integer 8 operators, right? conv2d, different permutations of conv2d, as and concat, etc. Right? And in Q4 is when we're going to add even more operators, as well as some of the common BF16 operators. And the runtime API will be expanded to support Windows as well. We'll see actually the number of customers in edge applications still need Windows support and not just Linux. And in terms of the spec for the X1M M.2 card, this is a 6 to 8.2 watt TDP device in a 22 by 80 B plus M key factor, which we found to be the most popular one. Of course, there's 4 lanes of PCIe, and it's going to sample in Q3 with a production of Q4 with a 1,000 unit budgetary price of $399. So that pretty much wraps up the talk for me. If you have a high volume application and you want to start prototyping and evaluation, we'd like to show you how fast your model can run on the X1 chip. So please contact our sales VP, Dana McCarty, to run your TF Lite and Onyx model, and we can bring up to speed very quickly. Thank you very much. Well, I'm asked to rate my own talk. Sure.
Great, thanks, Cheng.
Thanks, Linley.
We do have some time to answer some questions now. So please submit your questions using the Q&A button at the bottom of your screen.
Oh, yeah.
Cheng, I just want to start with, you talked about the graph partitioning capability, which looks like a good way to improve throughput. But my question is, what is the effect on latency?
Yeah, so basically the main effect on latency, as I've kind of alluded to, is actually the time to transmit the activation from one chip to the next one. So that's one of the main reasons you do not want to partition too many times unless the graph requires you to do so. So you can view this as 2 solutions. One is you just run all the chips in parallel, executing the same graph, which avoids that latency hit of sending it from one chip to the next. But of course, you will not be able to cache as frequently, and you will have to fit the model onto the DRAM that you have. So far, unless we're exceeding 512 or a gigabyte of a model size, the DRAM usually doesn't become a problem. But beyond that, the partition becomes a requirement, in which case we have to find places where the activation can be cut at a small enough size, and generally, like I've mentioned, it kind of shrinks pretty quickly in the beginning of the funnel and then gradually shrinks a little bit more until the very end. And maybe it blows up a little in the end, but the middle part of it is usually pretty small in terms of the activation footprint compared to, say, the input image. So usually those places are not going to be a big hit on latency if we consider just 4 lanes of PCIe Gen 4, especially Gen 4, divided by the activation size, or the activation size divided by the throughput that the Gen 4 4 lanes can provide you. Yeah.
Right. And so, and you mentioned that the architecture has this ability to reconfigure the FPGA on a layer by layer basis. I mean, that seems to be kind of what differentiates
It's a
Flex
requirement.
Logix from most of the standard kind of ASIC based
Yes.
accelerator. So, I mean, it seems like a great way to optimize the architecture for each layer, but I'm wondering how much time do you have to spend reconfiguring each layer in between? I know a lot of FPGAs are pretty slow at that.
Exactly. So right, this is the whole reason why FlexLogix as an embedded FPGA company even went down this route, was when I was taking a step back in trying to apply FPGA technology to edge inference, right? I reached 2 conclusions. One is it must be able to reconfigure on the fly, because a lot of customers, in fact, most of them will just have one device. So you have to be able to not limit the size of the customer model. So it has to reconfigure on the fly. So what happened is, in the previous talk I've mentioned, right, as a layer is executing, it is prefetching the configuration bits for the next layer, so that when the layer has finished computing, it will only take, a few microseconds, in fact, to reconfigure the layer and then get up and running again. So say a model like YOLO, we are at something around 170 configurations to run one model. So, at 30 frames per second, that's about 5,000 reconfigurations. So each configuration is going to run for roughly 200 microseconds. So you talk about overhead, a few microseconds over 200 microseconds, you're talking about a couple percent of overhead. So that's the overhead we're speaking of. So of course, if you are trying to run 5,000 frames per second, then the overhead becomes much more significant. But in most real-time applications, obviously, you're taking, 10, 20, 30 frames per second times however many configurations this model needs. That's kind of how many reconfigurations per second they need to occur. And all that, of course, is seamless to the customer. But since you're asking about reconfiguration, that's what's happening in the background.
Right. Yeah, that's a pretty good trick. So, question from the audience: what is the performance difference between the M2 and PCIe cards?
Yeah, very, very good question. So obviously, the M.2 card is limited to 8.25 watt of throttling. So basically, if we're talking about a highly utilized model, YOLO, it will become, not beneficial to run more than 533 megahertz. Because even if we run faster, the driver is just going to have to wait for even longer between layers to not exceed the power envelope. So obviously the PCIe card is unlimited. So for a model that could run at 900 megahertz, it will do that. But if your end application doesn't require that, so basically you evaluate the design at 533 and it satisfies your latency and throughput requirement, then that's all you got to do.
Right. So, so would you say then the performance difference would basically be linear in terms of the power?
The performance difference will roughly be linear in terms of the power, yes. There is cases, for example, in fact, some models where the operator usage is more sparse, so that even the X1P1 card cannot use all the max and therefore the power isn't as high. So in those cases, if the X1P1 card already will not exceed 8 or 9 watts, then of course there is no difference in those cases between the M and the X1 and the regular half length cards. But most of the models, our Mac utilization is much higher, so we could exceed 8 watts on the X1P1 front.
Right. So the smaller card is good if you have a sparse model, or if you don't need to push the performance beyond what you would
a certain point, or like, the edge server example that I showed, that you're really just trying to maximize this for inferences per box instead of, say, inferences per card.
Right, right. Another question from the audience, does FlexLogic support TinyML?
I've actually not looked into TinyML, so I'm not sure if that is an exportable format or that is a particular model. If it's a particular suite of models, I would say no problem, right?
Yeah, I
Generally
think
speaking.
TinyML actually is actually more relevant for running on CPUs. I think maybe like TensorFlow Lite is, I think, more maybe what they're thinking of.
Yeah, obviously TensorFlow Lite is supported, and that also obviously runs on both CPUs as well as accelerators. That's how we even verify that our results are numerically identical to the reference. But yeah, sorry, I don't have much experience with TinyML.
Right.
Yeah.
And so, what frameworks does the compiler support?
Yeah, so basically, generally, when we get the models from the customer, if they're in TF Lite, obviously it's generally coming from TensorFlow. If it's Onyx, what we have see just from the embedded data, generally it's coming from PyTorch. But obviously, it can come from others as well because it is an open network exchange format, right? So there is no limitation to whether it's Cafe or PyTorch or something else. But that's just what I've seen so far. Again, we're not trying to sell you an integrated design environment. We are trying to get you to use existing ones because you already have your models up and running, and just export them to this format so then we can take it with little to no work from the customer.
Right. Another question from the audience. Can you put a SATA power connector on the M.2 card?
I'm not sure why we need that. That's really a question for the systems engineer, but I'm not sure what the benefit of that would be. Right now, obviously, once we plug it in, we get power directly from the slot, and that's why we don't exceed a certain power budget, because the PCIe obviously is limited to 75 watt, and we're not close to that. But the M.2 form factor have strict power requirements, right? I thought the power connector is if we're exceeding it, so you kind of had to augment the power from some auxiliary sources. But sorry, I've never had a need to use any kind of additional power connector to use with our device.
Okay, well, thanks, Cheng. We're out of time.
Okay.
Can you take down your screen share?
Okay,
so
yes.
We can make room for the next presenter. And thanks for the presentation. Cheng will be appearing at a breakout session in just about 30 minutes. So if you have any other questions or you want to see the demo, please come by and see him there.